All right. So I would wait here for like a few minutes so that everyone can join and then we can start. So this is our part 18 of our discussion on control system engineering, and regarding root locus technique, this is going to be our first discussion. We're going to have 3 classes on root locus technique. That's part 18, and today we're going to discuss root locus technique, as I said. All right. All right. So I would start by mentioning that I asked you to remember something in our last discussion, during our last discussion. Okay. Last we discussed conditional stability through the Routh-Hurwitz technique, and there I asked you to remember something. Okay, keep something in mind. Keep what in mind? A particular, very particular example in mind. So let me bring that example up. Okay, that we did in the last class. Hold on a second. Let me save this file. All right. All right. So this was what we did in the last class. So we discussed conditional stability, right? So we figured out under what condition a system is stable. Okay, under what condition is not, a system is not. Okay, something like that. And I asked you to remember an example like this one. Okay, remember this example. All right, I asked you to remember this example. Okay, so this was an example of a system for which the system was stable under a certain condition and the system was unstable under certain other conditions, right? We also saw some other examples as well. Okay, right? But try to understand that in this condition, so under, for example, with this particular example, okay, we saw that the system was stable when k was below 60. The system turned out to be unstable when k was above 60, and at k equal to 60 the system was marginally stable, right? So these are the things that we actually figured out in our last discussion, right? That was something we did figure out, right? Nice. So we did figure out something like this. But would it not be nice if we could figure out the sort of more or less relative, or rather more or less exact pole locations for different varying values of gain k? Right? Wouldn't it be nice to know the changes in locations of the closed loop poles when we vary the value of k, right? Here in this one, we already know that for a certain values of k, the system is stable, the closed loop system is stable, so the closed loop poles are behaving certainly, or rather they are on the left half plane. For certain values of k, the closed loop poles are on the j omega axis, and for certain values of k, the closed loop poles are on the right half plane. But would it not be nice if we knew exactly how that change happens, right? How that change happens. Essentially, we can say when I am changing, say for example, when I'm changing my gain from a very low value up to 60, then of course the locations of the closed loop poles are definitely changing, right? Right. So the locations of the closed loop poles are definitely changing. Has to be changing, right? Because the gain k would change the locations of the poles. That's quite obvious, right? So today, in Evans root locus technique, was this technique was derived by Walter Evans, and unfortunately in control engineering, we often attribute different technology after their inventors, right? We say Bode plots, okay, named after Bode, who invented it. We say Nyquist plots, those are invented by Nyquist. Nichols chart, invented by Nichols, okay, and Routh-Hurwitz table, for example. So things are named after their inventors, but unfortunately, root locus is not always associated with the name of the inventor. But that is why whenever I teach root locus, I try to remind people that it was derived by an electrical engineer and avid mathematician, or Walter Evans. He was also a pretty good businessman as well. Okay, and back in those days, again, the entire emphasis was on the fact that people didn't have calculators, right? Let alone even computers, right? So the way it was devised was that you should have a technique that would allow you to see how the locations of the closed loop poles would change depending on the value of k, right? So if you increase the value of k, how would the locations of the closed loop poles change, right? Of course, if I vary the value of k, the locations of the closed loop poles would change. But how would they change? If we could figure that out without actually calculating the poles for different closed loop poles for different poles for different values of gain k, okay, that would be pretty useful, right? To exactly figure out. And now, why do we need to figure out the exact locations of the poles? Because we are not satisfied by just knowing the stability of the system, right? If we know the system is stable, if we know this system is unstable, that's not enough for us, really. Okay, think about that, the design problem you did, right? If you just designed, so you are supposed to design um, a second order system, okay, essentially a transmission system, right? A suspension system for a vehicle, right? So in there, you saw that just having a stable system is not enough, right? You have to also optimize certain things, right? You have to make sure that the settling time is small, okay? You have to make sure that the rise happens more smoothly. You have to also make sure that the peak overshoot does not go beyond a certain prescribed value, such and such, right? Those are determined by the undamped natural frequencies present in the system and also the damping ratios, right? And undamped natural frequencies, damping ratios, these are determined by the relative pole locations. Now we had drawn different circles and radial lines on our axes, okay, earlier, and we said that that was our S grid, okay, if you recall. Okay, so let me just bring that up. Hold on a second. Not this one. All right, so that was this one. All right, all right. So I think you have this, right? You already remember this, right? So this is the S plane, right? This is the S plane. So real part of S and imaginary part of S, and pole locations relative on this. So basically, if I have a pole pair somewhere like here, okay, by looking at this S grid, this is again called the S grid, okay, grid on the x-axis, grid on the S plane. So by looking at the relative pole locations, we would be able to determine what undamped natural frequency the system has, rather what undamped natural frequencies the system has, and also the relative values of the damping ratios for those pole pairs and everything, right? So those can be determined, and based on that knowledge we can swiftly determine how much overshoot there would be, how slow or fast the response would be, such and such, right? So we can figure those out. See, that's quite important. Besides knowing whether a system is stable or not, this is the second most important thing you need to remember, right? Or rather, the next few most important things. Okay, the first and foremost, you need to remember, you need to figure out whether the system is stable or not. If it's an unstable system, we don't want to deal with it unless we can stabilize it. Okay. Other than that, we only deal with stable systems, and on top of that we want to figure out how the system behaves besides stability, right? Just having stability is not enough. Just having stability is not enough. We have to also live happily, for example, right? So that's gonna be the purpose of this one. Okay, so let's go to our particular discussion today, right? And just as usual, the kid has started shouting the moment I started teaching, unfortunately. Anyway, so remember our transfer function. Okay, remember that our example, our very nice and particular transfer function. Let's draw that. So this was our closed loop system. It was a unity negative feedback closed loop system. And the transfer function was k divided by, again we discussed all these things, so I am not going to discuss these things once again. Where does this k come from? You already know by virtue of the last class we had, right? I suppose. So I cannot repeat myself today at least. Okay. Imagine we had h here, but for the moment consider h is equal to 1. Okay. So whatever we're going to discuss will be applicable if I have h here. Doesn't matter. Wouldn't matter. Right. So this is the reference signal. This is the controlled output value. Okay. This is your forward path transfer function. This is your feedback path transfer function, which is in particular here is 1. Okay. And there is nothing else we need to point out at this particular moment, right? So we know what the closed loop transfer function looks like. So the closed loop transfer function is the transfer function between CS and RS. Okay. And that is GS divided by 1 plus GS HS. Okay. And here, if I just do the calculation here, so this would become K divided by S plus 1, S plus 2, S plus 3 plus K. If you just do the simplification, you'll see that has to be the answer. Right. So the closed loop, so this is the transfer function of the closed loop system, right? This is the transfer function of the closed loop system. So the closed loop poles are determined by the roots of this polynomial. Whatever polynomial this one is, the closed loop poles are determined by the roots of this, right? All right. So this is known as the characteristic polynomial. So we write that the characteristic polynomial is this one, right? S plus 1, S plus 2, S plus 3 plus K. Let's just simplify this a bit further, which is, this is like S square, sorry, S cube plus, what was it then? 6S square plus 11S plus 6 plus K. And we like to combine these two terms. So that's K plus 6. So that's your characteristic polynomial. So where are the closed loop poles? We would say that the closed loop poles, which not only determine the stability but also determines how the system behaves, how the damping ratio behaves, okay, how the undamped natural frequencies behave and everything, right? So for the most part, the closed loop poles determine how the system behaves in terms of stability and in terms of its performance, right? Now the closed loop poles themselves are determined by solving the characteristic polynomial. So essentially, characteristic equation I would write, characteristic equation, which is the characteristic polynomial equated to 0. So essentially the roots of the characteristic polynomial. All right. I don't think there is any confusion here. But now try to understand our position here. Of course, by virtue of Routh-Hurwitz, we know the ranges of gain k for which the system is stable, for which the system is unstable, such and such. But we don't really see how changes in gain would result into changes in the locations of the closed loop poles. We don't really see that. Do you understand my point? Okay, we don't really see how the changes in gain k results into changes in the locations of the roots. Do we see that? No, we don't. Right? How the roots behave really. Okay, all the intermediate values, we know the system is stable as long as k is a positive number and less than 60. Okay, but how stable, rather not how stable, we shall discuss how stable later on, but how does it behave really? Okay, what about the damping for different values of gain k? Okay, would the system behave the same way for gains k equal to 20 and k equal to 5? Would the system behave the same way for these two values of gain? Okay, so we have to figure these things out, right? Okay, as engineers we are not only not happy by just knowing that the system is stable, we also need to figure out the other characteristic features of the system, right? But the point again stands, without calculating much of anything. Okay, if we wanted to calculate the exact values of the roots, we could, okay, by placing different values of k here and solving the equation, right? So it's a third order equation, and solving third order equation is not very difficult task. Okay, you can employ a combination of bisection method and your Newton-Raphson method, and you can numerically figure out all the solutions happily, quite easily, for different values of k. Just plug in different values of k, start with k equal to 0 maybe, okay, and then keep on increasing value of k with suitable intervals, and with that, as you go on increasing the value of k, the roots will change, and then you can just plot the roots. That, if you do, what you get is called the root locus. So locus of the roots, essentially locus means path a point takes. So roots are essentially points, roots are essentially the poles, poles are essentially the points. The points the poles take when I change the value of k. That's called the root locus. So roots are essentially referring to the roots of the characteristic polynomial, and locus, their locus, the path they take, okay, when I change the value of k in k, rather increase the value of k in k. Okay, that's called the root locus. And really actually it should be root loci, because of Latin, you can understand. Okay, loci is the plural of locus. In any case, you can call it root loci, you can call it root locus, right? You can call it whatever you want, right? Hold on for a second. What did I just do? All right, I will check that later. All right. All right. So again, if you have any problem, difficulty understanding anything, try to ask. Okay. Now I would try to keep my discussion brief, but again, if I move too fast, it might be difficult for you to understand what I'm saying here. All right. But let's start with k equal to 0. Let's calculate that, because we can easily calculate that actually, really. Okay, let's start with k equal to 0. Again, our objective is to figure out how the poles move, really. Okay, how the roots of the characteristic polynomial move, okay, depending on different values of k. Now let's start with k equal to 0. Now if I say k equal to 0, what does the equation look like? Now the equation looks like s cube plus 6s square plus 11s plus 6 equal to 0. Now of course we know the factorization of this. How exactly do I know the factorization of this? From this, we know that s cube plus 6 s square plus 11s plus 6 is essentially factorized into s plus 1 times s plus 2 plus times s plus 3. So that equation basically turns out into s plus 1, s plus 2, s plus 3 equals 0. So I already have the roots of the characteristic polynomial. So we are solving this equation, again keep that in mind. We already have the roots of the characteristic polynomial for k equal to 0, and for k equal to 0 they are at -1, -2, -3. But keep in mind, this is a very pretty example I chose. Okay, but in real life things are not as pretty as the examples you study in class, right? Anyway, but again, think one very important point to remember is that what about the forward path transfer function itself? What about GS itself? Look at GS itself, and if you look at GS itself, the pole of GS itself are at -1, -2, -3. GS is known as the forward path transfer function, also known as the open loop transfer function. Okay, so this is the open loop transfer function, and what are the poles here? The poles are at -1, -2, and -3. Okay, and these poles are identical to these poles. And again, we are right now discussing a situation where h is equal to 1, and we shall discuss the generalization when h is something else. Okay, just keep in mind. So the forward path transfer function's poles -1, -2, and -3, these are the poles of the forward path transfer function, are identical to the poles of the closed loop transfer function when k is equal to 0. So that is something we just figured out. Okay, now instead of drawing this on a paper like this, let's do that computationally. Since we have a programming language at our disposal, we can actually figure these things out computationally. So let's try doing that instead here. Okay, and let me see what we can do with this. All right, so let me just switch to this. I just scratched up this program this morning, really. Hold on for a second. All right, so I think you can see this, right? All right, so somehow I started with a different transfer function. Actually, exactly forgot what I gave you. That is 6, that's 11, gonna be k plus 6. Right, let's see how it looks like. All right, so I have to move it in this direction, so let's do that. Let's make this 10. No, that's 6. Hold on for a second, huh? Okay, that's gonna be minus. Here there will be 5, say. Okay, so I think it's visible properly, right? Okay, so you can see these are the pole locations when k is equal to 0. So I have a slider for k. Okay, I have a slider for k, and you can see the pole locations here. I think that's pretty nice, right? So we see that the one of the poles is at -1, one of them is at -2, one of them is at -3, and again these are the particular lines here, right? So this is the real line here, so this is real part of s, and the vertical line is representing the axis for the imaginary part. So that's the j omega axis, right? So that's 0, right? I think you can you people can see this, right? No issues. So k is equal to 0. Let me just hold on a second. You toggle here. All right. So that's fine, right? I think. Okay. So that's for k equal to 0. So here I have k equal to 0, right? So here these are the relative pole locations. These are the actual pole locations. So here the poles are at -1, -2, and -3. All right. So here are the poles. I think there is no complications whatsoever with this. All right. So let me just edit this a slight bit more, because I want this to be more or less perfect to some extent. Again, make this I'm not sure entirely. I'll just, okay, fine, we shall modify this as we need it, right? So that's fine. All right, so these are the relative pole locations. Again, I believe you don't have any difficulty understanding this. All right. All right, so now what if I go on increasing the value of gain k? Now Now there is a problem. Say my next choice of value for k is, say for example, say 0.1. So imagine I am increasing the value of gain k in the steps of 0.1 maybe, okay, in the steps of 0.1. So under this condition I want to figure out the exact locations of the poles. So what is the exact location of the pole? So I have to solve for this equation, s cube plus 6 s square plus 11s plus 6 plus 0.1. So that was the thing, right? 6.0 plus 0.1. So it's essentially this is 6.1, right? That's equal to 0. Now we have to solve for this. Now this does not factorize into this pretty factorization, right? It does not factor into this pretty factorization anymore, right? So now you have to employ numerical methods to figure out the pole locations. But you can use numerical methods to figure out the pole locations, right? Because it's a third order polynomial, not that difficult really. Okay, you can use factorization, sorry, you can use numerical methods to figure out the solutions of this, but the solutions of this would give you the new pole locations, right? So now let's look at our plot once again, because I don't want to compute this numerically or ask you to calculate this using a calculator or whatsoever, but we want to see at least how that behaves. Okay, so again, this was our system here. Okay, and let me just do one important thing here. Okay, before I just go further. Hold on for a second. All right. All right. So now these poles are for k equal to 0. Nice. We can at least see the value of k here. Right now. All right. Nice. Now let's increase the value of k to some extent. Let's make this 0.1 as I did. So remember the pole locations exactly. Now increase the value of k. See? Did you see the change? Let me do it once again. So this was the pole location for k equal to 0. Now let's increase this to k equal to 0.1. Notice very carefully at the pole locations. Notice very carefully. See? So this pole moved to the left, this pole moved to the right, and this pole moved to the left. Okay? So try notice very carefully. So the poles were originally at -3, -2, and -1 when k was equal to 0. But the moment I increased k, what happened? This pole moved to the left, this pole moved to the right, and this pole moved to the left. Now notice very carefully once again. Say if I increase the value of k slightly beyond, so if I make k equal to 0.2, notice very carefully again. Very careful, huh? See, the pole now moved to the right, this pole now moved to the left, and this pole again moved to the left. Right? Did you see that? Nice. So let's now increase the value of k smoothly. Okay? Let's do that. So this is how the poles are moving. See the value of k here? As the value of k is changing, this is how the poles are moving. This pole is moving in this way. This pole somehow they manage to meet at a certain point and then diverge, become complex conjugate, and now they are going away, right? So let's now make this maximum value not this but maybe 80 or something. Okay, and make the step size not this but say this. All right. All right, so now let me increase the value of gain k and see how the system behaves. See, the poles started approaching each other and they met at a certain point and then they diverged. Let me show you that particular story first, maybe. That is again, I am decreasing the gain k here, right? See? Okay, so let me show you that particular story here. So up to say gain, I think gain 1 maybe. Step size 0 0 1 will be nice, right? All right, now look at this. Okay, I'm increasing the value of gain k. As I'm increasing the value of gain k, see, the poles are approaching each other. So these two poles are approaching each other. This pole is moving in this direction. Okay, these two poles are approaching each other as I'm increasing the value of gain k. And then at a certain value of gain k, see, hold on, I just crossed the value. I just crossed the value. Let me go back. Was it 4.2? No, it's I think 3.8. Okay, somewhere between 0.37 and 0.38, somewhere between 0.37 and 0.38. See, somewhere between 0.37 and 0.38 value of gain k, the roots meet. These two poles meet. Okay, this was approaching this direction from here, and this pole was approaching this direction from here, and they meet at somewhere between 0.37 and 0.38 value of gain k, and then after meeting they diverge and they become complex conjugate pole pairs. Okay, so let me show their path with a higher value of gain k here, say 80. I think that computation needs to complete first. All right, so let me show you how it behaves. Now essentially what happened, once again, let me just go back in the plot here. Essentially what happened, they met at this point and this pole diverged, and this pole went to that direction. So let's increase the step size here. Let's make this 0.1. Okay, and let's move this. So that is something happened. Now as k increases, you can see this is the behavior of the poles. Now interesting thing at k equal to 60, right? Let's fix this at 60. So see, k increasing, right? As k increasing, this pole is going this way, that pole is going this way, that pole is going this way. Now what about k equal to 60? Okay, it went a bit beyond that. Okay, what about k equal to 60? Look at k equal to 60. At k equal to 60, this pole is here, this pole is here, and that pole is all the way there. Okay, it's going to go beyond -6 here. So essentially this pole is going to go beyond our plot here, but you can see that this pole is here, this pole is here. Okay, so k equal to 60 did gave you a marginally stable system. Now if you go beyond that, then that pole went beyond our plotting range here. So that pole is not missing really, but that pole is there essentially outside our plot. But look at these poles. These two poles crossed the j omega axis that way. Again, go on increasing the value. So that pole is still going in this direction, and this pole is actually have crossed the j omega axis and going its merry way, right? So I think you can understand the concept of root locus here. Root locus gives you a sketch of how the roots move depending on different values of gain k. That's the whole idea here. Okay, so they figured out a way of analyzing how the roots behave, how the roots move for different values of gain k. As I increase the value of gain k, how the roots change their locations, how the poles change their location. That's the important point. But again, we are going to learn the technique of root locus, in which we won't calculate the roots. Instead, we would figure out a way of drawing the root locus without actually really calculating the roots for different values of gain k. With that said, let's jump into our actual discussion today. All right, so we increase the value of gain k. Now we have to solve for it, right? And as such, we have to then increase the value of gain k. Beyond that, we have to keep on doing that, right? So so we have to do 0.3, 0.4 and so on, okay, something like that, and maybe up to 80, something like that. Okay, so beyond the gain at which the system becomes unstable, okay, so something like that. For all these different values, you can see how many calculations we are doing. So if you are taking up step size of 0.1 and going up to gain 80, okay, so we are doing 801 calculations, 801 root findings. So for one particular value of k, you are solving this equation once, right? But if you choose 801 different values of k, then you have to solve this equation 801 times, okay, and then you can plot the locations of the roots, and then you can join them with a certain smooth curve, and that would be a root locus. That would be really difficult, right? Really difficult for us. Okay, so now let's take insights from our from what we discussed and construct the root locus, but using techniques that does not involve computing all these things, right? Right. So let's bring this up. Let's make this page. Okay, let's take a new page, I think. Okay. All right. Let's take a new page here. Let's make this page a graph paper. All right. Okay. Okay. It did not forgive me somehow. Okay. That's the real part of S. That's the imaginary part of S. Of course, so real part of S is often called the real line, often represented through sigma, and the imaginary part is the imaginary axis is the j omega axis, often just represented as j omega. All right, and this is of course the S plane. Okay, all right. So let's start. Let's start with the very discussion we had. Okay, we saw that when k was equal to 0, the roots were at -1, -2, and -3. So here, or did I draw it correctly? No, I don't think so. Hold on for a second. Here, here, nice. So these are the roots, or these are the pole locations when I started with gain k equal to 0, right? That was fine, I think. Okay, this is for gain k equal to 0, right? All right, so these are the three poles for gain k equal to 0. Now as I increase the gain k, what happened? We saw, I mean, I would ideally in a physical class, I would ideally ask you to bring your calculator and solve for every value of k. So here I'm not doing that. But now see, as I increase the value of gain k, what happened? This root moved in this direction, this root moved in this direction, this root moved in this direction, and this root actually moved in this direction, right? Right. So what happened was that this root moved in this direction, okay, this root moved in this direction, and at a certain value of gain k they actually met. Okay, you know what, let's remove this graph, and I think the axes are not suitable for your plot here. Let's make this slightly different. Okay, let's take more space, what I mean. Okay, that's pretty thick. Hold on, huh? So whenever I'm doing things manually, you have to be patient with me. Okay, I think I can move this even further. Can I though? Can I though? No, unfortunately there would be a problem with that. Okay, let's deal with what we have, because we are going to face certain unfortunate problems regarding the plot here, but no problem, we can manage that later on as we face the problems. All right, let's see. Right. So as I said, as you saw, as the gain was increasing, this pole was moving in this direction, this pole was moving in this direction, this was moving in this direction. Yes, absolutely. It's absolutely possible to draw it using Python, and I'm going to teach you that by the end of this class. By the end of this, you would know how to draw this using computer Python, right? So now we saw that this pole would be moving in this direction, this pole would be moving on this direction, this would be moving in this direction. Now as k increases, right? So we are saying that these are the initial locations of the root, okay? And as k increases, this moves in this direction, this pole moves in this direction, and they meets at a certain point. I'm not really entirely sure right now what point they meets at, but they does meet at a certain point. Okay? So there is a point at which the system is critically damped. Really, we have two pole pairs on the real axis that are equal. So this root is moving in this direction, this root is moving in this direction. They meet at a certain point. Now after meeting at that certain point, what happens is now they diverge. So this root, one of the roots now move, one of the roots would then move in this direction, okay? One of the roots will start moving in this direction, one of the roots will start moving in this direction, and this is again moving in this direction forever. This particular root is moving in this direction forever, okay? So the roots will start moving in these two directions here, right? And eventually what would happen is that one of the roots from here would cross the geometric axis like just like that, okay? You saw that. So this was kind of the path traced by the roots, okay, if you notice that plot carefully. And the other root would trace this path, and of course this root would trace this path, right? So we would be able to see that when k was equal to 0, when k was equal to 0, the roots were here, here, here. So for k equal to 0, the roots were at s equal to -1, s equal to -2, s equal to -3. Now as the gain increased, they met at a certain point, and from there, as k increased to infinity, they went beyond the geometric axis like that. But right off the bat, we know a few more things. We know a few more things. We know exactly when this happens. We know exactly when the poles are on the, we will know exactly when the poles are on the geometric axis, right? We know exactly when that happens, right? So we know exactly when k is equal to 60, the poles are on the geometric axis. We know exactly when k is equal to 60, the poles are on the geometric axis. And you also know the exact locations of the poles at that particular point. Again, through Raoult-Hurwitz technique, we already know quite a bit about the system, right? Quite a bit about the plot. Now let's try figuring out how this can be generated by doing some very simple manual calculations, right? So let's first and foremost, let's talk about the rules of root locus. Rather, I would say root loci, okay? So rule number 1, and that's the most important rule you should never forget, is that root locus root loci rather I would say, are symmetrical about the real axis. Okay, so rule number one says that root loci are symmetrical about the real axis, and that has to be true, right? If I give you a polynomial, say for example, if I give you a polynomial and ask you to solve, okay, ask you to solve for it so that you find the roots. Now it's a third order polynomial, right? You are going to get three solutions. One of them will have to be real, and other two can be a conjugate pair. Conjugate pair can be a complex conjugate pair, can be real numbers, right? So try to understand. If they are real numbers, all real numbers, then they are lying on the lying on the real axis. And if one of them is real, which I can see this one is real always, okay, this root is real. And if the other two are conjugate pairs, then again conjugate pairs, right? Conjugate pairs, which means if one of the poles are here, then the other pole would be here. If one of the poles are here, then the other pole would be here. What I mean is that the roots will always preserve a symmetry about the real axis. Roots can either be real, so roots can either be on the real axis, or they can be complex conjugate pairs. So they are symmetrically, so they are equally apart from the real axis, right? So root locus is always going to be symmetric about the real axis. So if you can draw what happens on top of the real axis, then the bottom of the real axis will just be a mirror image, right? Because the poles are either real, so they lie on the real axis, okay, or they are complex conjugate pairs. So if one of the pole is this distance apart from the real axis on top, then the other pole corresponding to that would be this distance apart from the real axis below, right? So root locus is always symmetric about the real axis, right? If you draw a root locus that kind of let me say, if you draw, so this is the axis, if you draw a root locus, say that looks like this, something like that, maybe something like that, okay, then it's a wrong root locus because it's not symmetrical about the real axis. That's never going to happen, right? So roots cannot be unsymmetric in nature like that. Roots can either be, roots of a polynomial with real coefficients can either be real or complex conjugate pairs, okay, and as such the root locus is always symmetric about the real axis. So this is quite understood. That's rule number one. Now rule number two is slightly more difficult to understand, but let's see how that is that can be derived, how that can be derived, okay? So this is the rule of symmetry. So we would have 10 rules regarding the root locus, and we would say, so this is the symmetry rule, rule of symmetry. Rule of symmetry. Now rule of say, I would say on the real axis. I am writing the rule here, but we will see how that has to be true. Okay, rather let me just say something very important. So again, what equation are we solving again? We are solving this equation, right? So try to understand once again. The equation we are solving here. So the closed loop polynomial here, closed loop transfer function here is gs divided by 1 plus gs hs, right? So now let's say gs is equal to this. Instead of saying this is k, let's say this is 1 and we had a k block here, right? Just like previously we said we had a k block here, right? Something like that. If we imagine our system like that, okay, then we can rewrite our equation like this as such, right? Now look at this exact polynomial. So if I ask you on this exact polynomial, what is the characteristic polynomial here? What is the characteristic polynomial here? Rather, what is the characteristic equation here? So what is the characteristic equation? So in this transfer function, what is the denominator really? That's 1 plus k times gs times hs. So that's your characteristic. If I equate that to 0, so that's your characteristic equation really. And you can verify that 1 plus k gs hs equated to 0, that's your characteristic equation. All right, so I can say k times gs times hs, that's equal to -1. Okay, and again I can say gs times hs is equal to -1 by k. Now what is a negative number? So this is a complex number, right? gs is a complex number, hs is a complex number, because s is a complex number and g is a function of complex numbers, so this is also a complex number, right? So these two are complex numbers. In complex numbers there is no question of negative, positive, larger, smaller. These things do not apply for complex numbers. But what is a complex, what is a negative number in complex domain, right? If this is the complex plane, then just a -1. What is a -1? A -1 is really 1 angle pi. 1 angle pi. Good morning. 1 angle pi, right? What is -1? -1 is just 1 angle pi. 1 angle, I would say 1 angle 180 degree, right? Just like that. So this is just like 1 angle 180 degree. You people know that already, right? So what is 1j? 1j is essentially equivalent to 1 angle 90 degree, right? What is +1? +1 is equivalent to 1 angle 0 degree. Okay. What is minus, say for example, what is -2? -2 is equivalent to 2 angle, sorry, not -2, -2j I meant to say. What is -2j? -2j would be 2 angle -90 degree. Yeah, you know that, know these things already, right? So with that said, with this knowledge we can, of course this knowledge is already something we have, we can say that this gs times hs, again this is a complex number, this is also a complex number, this gs times hs, this gs times hs is equal to 1 by k. Now remember, 1 and k, they are real numbers and they are also themselves positive numbers, times 180 degree, right? So we are representing everything in terms of complex numbers. Now there is a benefit of representing everything in terms of complex numbers, which I am going to go into shortly. Okay, but again try to understand, we are representing something like this. This is a complex number, so this number is, so this point, not writing, so this point is -1 by k, and we are equivalently writing it as 1 by k angle 180 degree, right? So it's a negative number and I'm representing that negative number with this complex notation, right? Complex notation. So I'm saying that -1 by k is essentially 1 by k angle 180 degree. But could I also equivalently say this is like 1 by k, so this is pi, right? Pi in terms of radians. So I can equivalently say that this is 3 pi. Same thing. Try to understand. If I say that this angle is pi, then of course I can go one round and here come back here. That's gonna be 3 pi. So that's equivalent. Also I can equivalently say that angle -3 pi. Also equivalently I can say that's 1 by k angle 5 pi. Also I can equivalently say that's angle 1 by k angle -5, 1 by k angle -5 pi. Such and such. These are all true, right? Really? So I would like let's write 180 degrees, but as long as we are consistent with our notation here, it's fine, right? So it could be any, essentially we can add it is essentially any odd multiple of pi, right? Any odd multiple of pi, or rather, sorry, yeah, any odd multiple of pi. So it's an it's essentially any odd multiple of 180 degrees, right? So it's essentially any odd multiple of pi, right? Got it? I don't think there is any difficulty understanding that. So I'm choosing 180 degrees, so I'm choosing pi, that because that's the simplest possible answer. Again, there's something I missed. This is also equivalent to 1 by k angle minus pi, the same thing essentially. Alright? So any odd multiple, any positive, negative, odd multiple of pi would do, right? Apart from 0. Now why am I writing this equation? Writing this equation has an advantage. Again, keep this plot aside because we are going to draw this plot again and again. Let's keep this here. Let's keep this here. Safe and sound. Alright. Now look at this equation. So that's a complex equation, right? That's a complex equation. Equation in terms of complex numbers, rather complex functions, right? What about this equation? Now a complex number can, say if I give you a complex number a plus jb and I give you another complex number, say for example x plus jy, and say for example if I ask you this, say which one is bigger, 2 plus 3j or 4 plus 5j? Which one is bigger? Which one is a bigger complex number? If you said this one was bigger, then you were wrong. If you said this one was bigger, then you are once again wrong. In complex numbers, you do not have equality like that. This is not greater than this. This is neither less than this. Complex numbers do not have Archimedean ordering like real numbers do, right? In real numbers, we can say this number is larger than this, depending on whether the point is on the right on the real axis or not. Complex numbers can only be compared in terms of their magnitude or phase angles and such, but they cannot be compared in Archimedean equality, Archimedean ordering. Compared in terms of Archimedean ordering. We say that for real numbers 2 is greater than 1. This is called Archimedean ordering, because on the real line 2 appears to the right on the real line compared to 1, and from that Archimedean ordering we do say that 2 is greater than 1. So this is called Archimedean ordering, but that Archimedean ordering does not apply here. Okay, so again, with that said, complex numbers do not have this kind of conditions, greater or less, something like that. Two complex numbers can be equal, and if I say I have a complex number a plus jb which somehow is equal to x plus jy, then this can only happen if a equal to x and b equal to y. These two conditions must satisfy together. So real part must match the real part and the imaginary part must match the imaginary part. But again, complex numbers do have a polar representation, right? So essentially, if I say a complex number is x plus jy, then this length, okay, this length, say if I say this length is r and this angle is theta, then this complex number is equivalently represented as r angle theta, right? If this length is r, which is the modulus of the complex number, here r is the modulus of complex numbers, modulus of the complex number x plus jy, and theta is the argument of the complex number. Usually if it is on the first quadrant, that's the principal value of tan inverse y by x. Okay, so principal value of tan inverse y by x. So essentially we know what these values are, right? Again, so this is the angular representation. So now if I say I have two complex numbers, r angle theta and p angle phi, and these two numbers are equal, then just as usual their real parts, their magnitudes must be equal, and also their phase angles must be equal, right? These two conditions must be satisfied together in order for the complex numbers to be equal, right? So with that discussion, now we can say this implies two things. This implies that the magnitude of the complex number, so r is essentially the magnitude, right? So this is again a whole complex number. Then the magnitude of this complex number should be equal to 1 by k in order for this equation to be satisfied. So this actually results into two equations, separate equations. The magnitude must be equal to 1 by k, and the phase angle, and okay, this is an and condition, and the phase angle of the whole thing, phase angle of GSHS, that should be any odd multiple of pi, right? That should be any odd multiple of pi. For the moment, let's just write n pi. This has to be any odd multiple of pi. So it could be 180 degree plus minus any amount of 360 degrees, right? And of course n, sorry, not n pi, sorry, that's going to be 2n plus 1 pi, any odd multiple of pi, right? So I'm saying n is any number, just put any number. Okay, so this becomes an odd number. 2n plus 1 times pi is an odd number, and that's fine, right? So this is actually really, this should be 2n, so this should be 2n plus 1 times pi, really. Okay, so I think I can get rid of these silly calculations, right? You understand these calculations, I hope. Please tell me if you don't. Complex numbers can be, two complex numbers can be equal, and they can be equal only if the real parts and imaginary parts, real part matches the real part and the imaginary part matches the imaginary part. Similarly, if the magnitude matches the magnitude of the other and if the phase matches the phase of the other. Now these two conditions together, okay, is known as the conditions for root locus. These two conditions together, if I take these conditions and paste it somewhere else, these two conditions together are known as the conditions of root locus, and here they have specific names really. This condition, these two be satisfied together, and this condition is called the amplitude criteria. Of course, the amplitude must be equal to the amplitude in that sense. Okay, amplitude criteria. And this is the criterion I'm writing because that's a singular. Okay, and this is the phase criterion. Sometimes let's just write magnitude criteria. That is what people write usually. And this is the phase criteria. Now here someone asked me a question a long time ago. What happens if k is negative? If k is negative, then I also have to put a mod sign here. If k is negative, I also have to put a mod sign here, and then subsequently the angle would also change. If k is negative, then you can see then this becomes a positive quantity. So instead of being an odd multiple of 180 degree, it becomes a even multiple of 180 degree. Okay, so that's something you have to understand. Okay, and then the angle criteria would phase criteria, or sometimes called the angle criteria. Phase is essentially angle. So essentially the angle criteria would change, okay, for negative values of k, but we don't deal with negative values of k, and as such I'm not writing a mod or changing this angle like that. So this is a negative because this number is negative, because this number is negative simply because k is a positive quantity. We're assuming that. So with the very thing we need to say that k is positive, we're assuming, okay, positive gains only. Now these two conditions must be satisfied together. Now sometimes what happens, one of the conditions can be so if I figure out pole locations that do not satisfy one of these conditions, then those cannot satisfy this equation because we are solving for this equation. Again, go back, this equation is identical for our example. For our example, this equation is identical to this equation. Excuse me. This equation is the characteristic equation of the closed loop system, and this equation is also the characteristic equation of the closed loop system, right? And these two equations are identical. So if you are solving for that equation, okay, solving for this equation, then look very carefully that these two conditions together must be satisfied. Otherwise, if any one of them is violated, then what would happen? The root locus, so that point cannot be on the root locus, cannot be a root. So let me tell you what I mean, okay, with the example we have in our hand. Okay, let's see. So that's the example we are doing. Again, I told you that I'm going to draw this again and again. So that's the sigma, that's the j omega, okay, real part of x and imaginary part of x, and we are the s, and this is the s plane. Okay, so what are the open loop poles? The open loop poles are at -1, -2 and -3. So these are for k equal to 0, k equal to 0, k equal to 0. When the gain is 0, so these are the pole locations. So that's s equal to -1, s equal to -2, s equal to -3, just like that. Now I told you that we already know that this pole moves in this direction. Okay, this pole moves in this direction and this pole moves in this direction. Notice the gap between s equal to -3 and s equal to -2. Question is, can we find a value of k for which one of the roots is between -2 and -3? Question is, can we find a value of k for which one of the roots is between -2 and -3? Can we? Answer is no. Okay, here is why. You'll see. Now look at a point here. Say I'm asking this, can we, question is this, can we find a value of gain k for which at least one of the poles are here? Can we find a value of gain k for which at least one of the poles are here. Okay, can we? Okay, then again we have another question. Can we find the value of gain k for which at least one of the poles are here? Again another question. Can we find a value of gain k for which at least one of the poles are here, somewhere here? Similarly, can we find a value of gain k for which at least one of the poles are here? So we are essentially checking the entire real line. Okay, so we're checking, can the pole, can somehow one of the roots be between 0 and 1? So this is s equal to 0, right? This point is s equal to 0. We're saying, can the roots be between s equal to 0 and s equal to 1? Can the roots be between s equal to -1 and s equal to -2? Can the roots be between s equal to -2 and s equal to -3? Somewhere between that, somewhere. So this is somewhere. Okay, and can the roots be between -3 and beyond? So less than -3 in this direction, right? So we are asking this question. Now, can we answer this question? Yes, already one of you know how to deal with that. Can we answer this question by looking at these two? Okay, without actually solving for this, right? Without actually solving for this. Now, here comes the interesting part. Okay, so what we would do, we would put this value here. Try to understand. We would put this value here. So what was the equation here? What was the equation here? So look at this equation. Look at this equation. Okay, look at this equation. For our particular example, what is GSHS? For our particular example, what is GSHS? So we are solving for one of the equations, let's say. Okay, so angle GSHS equal to has to be, angle GSHS has to be 2n plus 1 pi, any odd multiple of 180 degrees. Now what is angle GSHS? What is angle GSHS? So what is GSHS? GS was that transfer function, right? Apart from the k here, that was 1 by s plus 1, s plus 2, s plus 3. Okay, that was 1 divided by s plus 1, s plus 2, s plus 3. All right, and that has to be an odd multiple of this. That has to be an odd multiple of this. But my question is, somehow I have to figure out the angle here, right? I have to figure out the angle here. All right, I have to figure out the angle here. Now question is, what is the angle of this? Of course, this is like 4 complex numbers. 1 divided by this, this and this, right? So we know that the angle of Z1 by Z2 is angle of Z1 minus Z2, angle of Z2. Of course, we have to do a plus minus pi in order to preserve the principal value. But I'm assuming that everything is preserved. And again, since we have an addition here, it doesn't matter. If you don't know what I just said, you don't have to bother. You have to understand that this is essentially equivalent to writing angle of 1 minus angle of s plus 2 minus angle of s plus minus angle of s plus 1 minus angle of s plus 2 minus angle of s plus 3, and that has to be an odd multiple of 2n plus 1, so odd multiple of pi, right? Now what is the angle of 1 in a complex numbers? What is the angle of 1? Of course, angle of 1, so 1 is on the right, okay, on the real line, so angle of 1 is essentially 0. If this was -1 or something, angle would have been minus 180 degrees, right? So I don't know these angles, so let's just write them as such. So minus angle of s plus 1 minus angle of s plus 2 minus angle of s plus 3, and that has to be 2n plus 1 times pi. But what is this angle I'm writing? What is this angle? Okay, what is this angle? Let me just say right now, what am I saying? What am I putting here? What value am I putting? I'm trying to figure out whether any value between 0 and 1, any value between 0 and 1 can satisfy this condition or not. Okay, my question was, for this point, look very carefully, my question was, can I find a value of k, any value of k, for which at least one of the roots is between 0 and 1, minus 0 and minus 1. Okay, can I find any condition for which at least, say, for which one pole is between 0 and minus 1? Okay, can I find a condition like that? Okay, so now how would I check in the reverse way? let's consider any value between 0 and -1. Okay, let's consider any value between 0 and -1, and let's put that here. Okay, my question is now can S be between, now can S be between 0 and -1, -1 and 0? Can S be between -1 and 0? Now I would right now ask you to give me an example, give me a value, exemplary value. Example, S equal to something between 0 and -1. So I'll take an example and show you whatever example you give me tells you something very interesting here. So give me any value between -1 and 0. Please be quick. Give me any value. Very quick. Whoever types it first. Oh, -half. Nice. Okay. You already told me -half. So whoever typed it first. Okay. You'll see whatever value you give me here will turn out to have the same result. Okay. So S equal to -half. Let's just write that. So S equal to -half. So we already have 0 degree. So now we are writing this equation once again. We are writing this equation, this very equation. So minus half plus 1, angle of that, minus half plus 2, the angle of that, minus half plus 3, angle of that. Now this has to be something, this one. Let me just simplify the left hand side, then I'm going to write down the right hand side. Okay, all right. So this is equal. So we're just calculating the angle, calculating this part, and then we are going to equate to this part and solve and see whether that's true or not. Okay, so this is equal to minus angle of 0.5 minus angle of minus angle of, how much is it? Minus angle of 0.5. What is the angle here? 1.5. So minus angle of 1.5 minus angle of 2.5. Okay, now question is what is the angle here? What is the angle of 0.5? Think about complex numbers. What is the angle of 0.5? So 0.5 is the number here. What is the angle in terms of complex number? That's 0.5, 0 degree, right? 0.5, 0 degree, right? So 0 degree, right? Minus, so minus 0 degree, minus. What is the angle here? What is the angle of 1.5? Positive number, 0 degree. What is the angle here? Positive number, 0 degree. So what is the total angle? 0 degree. Now question, is 0 degree, okay, is an odd multiple of this? So is 0 degree an odd multiple of 180 degree? Can 0 degree be an odd multiple of 180 degree? Question is, can 0 degree be an odd multiple of 180 degree? Because that has to be the thing, right? Okay. Can 0 degree be an odd multiple of pi or 180 degree? Please, someone tell me whether 0 degree can be an odd multiple of 180 degree. See, 0 degree could be an even multiple of 180 degree because 0 itself is an even number. Okay. So we could multiply 180 degree with 0 and we would get 0. 0 is an even number, right? Anything after division with 2 does not leave a remainder is a 0, is an even number, right? Is an even number. So 0 could be an even number, even multiple of 180 degree. But is 0 an odd multiple of 180 degree? Of course no, right? Of course no. 0 is not an odd multiple of 180 degree. And as such, this is an inequality. So I can say this is never going to be an odd multiple of 180 degree. So this equation cannot be solved. This equation cannot be solved by any point lying between this. So if I have a point that is between 0 and 1, that point can never be a solution to this, can never be a solution to the angle criteria. And I told you that it must satisfy the magnitude criteria and the angle criteria together in order for it to be a solution, right? Any point lying between 0 and 1 cannot satisfy the angle criteria, and since it cannot satisfy one of the criteria, that can never be a solution to the original characteristic equation. This was the characteristic equation, and here in our particular example, this was the characteristic equation. Okay, this was the characteristic equation. So any point lying between 0 and 1 in this particular example cannot satisfy the characteristic equation because it will not be satisfying the angle criteria. Okay, let me see another example. So this is, I'm saying no, it does not. What about this point? What about this point? So a point between -2 and -3. A point between -2 and -3. Alright. A point between -2 and -3. Does this satisfy the angle criteria? Or rather, can this satisfy the angle criteria? Now, someone other than the person who told me the previous value. Now, question. Can S between -2 and -3 be on can satisfy? So someone saying, okay, I said other than the person who told me the previous value, someone else choose a value between -2 and -3. Anything else? Anything between -2 and -3? Anyone else? Okay, -2.1, right? So -2.1. And again, just the previous thing, just keep in mind, this just does not apply in particular for S equal to -0.5. Okay, it will be applicable for any value between 0 and 1. So this is what we just said is applicable for any value between 0 and 1, right? Similarly, what you just said will be applicable for any value between -2 and -3. Okay. So now let's try to write down this equation once again. So let's just copy this and paste this value. Okay, we are writing this. So on this equation, we are putting S equal to -2.1, right? So again, forget the right hand side. So let's calculate this first. S equal to -2.1. So that's becoming -1.1 minus angle -0.1 minus angle 0.9, right? Okay, right. So now, sorry, there is a minus sign already. Minus. Okay, sorry, there is a minus sign. Okay, all right. So of course you can do the same thing with the values you are giving me. Someone said -2.7. A very similar thing will happen here. Okay, minus sign. Now what about this? That's a negative number. Yes, you can. Someone is saying we just checked for -0.5. How can we conclude for other values? You can. You use some other values, say 0. So you start with -0.1 and go up to 0. Say for example 99 -0.99. You will see that this is a positive. This turns out to be a positive number. So try to understand. The point is, if S is between 0.0 and -1, then this is a positive number. Then this is a positive number. If S is between 0 and -1, this is a positive number, right? So positive number has an angle of 1, angle of 0. If S is between 0 and -1, this is also a positive number. This is also a positive number. And if all of them are positive numbers, all of them have an angle of 0. So -0, -0, -0. So total angle is 0 degree. And since total angle is 0 degree, it can never be an odd multiple of pi. And that is going to be true for any value between 0 and -1. If I take a value of S which is between 0 and -1, then all these values are going to be positive. And since all of them are positive, all the angles are going to be 0 degrees. And as such, this is actually true for any value between 0 and -1. And just like that, if I choose any value between -2 and -3, any value before any value between minus 2 and minus 3, this is going to be negative. For any value between minus 2 and minus 3, this is going to be negative. Any value between minus 2 and minus 3, this is going to be negative, and this is going to be positive, right? And I know negative angles, real numbers have particular angles, and positive real numbers have particular angles. So it's a negative real number. For any value between minus 2 and minus 3, that's going to be negative. S plus 1 is going to be negative. So it's a negative 1.1. So what is the angle? Of course, the angle is 180 degrees, right? Right? So angle is 180 degrees. So let's write pi. I'm mixing and matching pi and 180 degree. You can understand that it's fine, right? Sorry, it's pi, right? Yeah, it's pi. Minus. Let's just say pi. Who cares? Okay, all right. Minus. What about this? This is again a negative number. Okay, something like this here. What is the angle? Angle is again pi, right? So pi. And this is a positive number. What is the angle? 0. So what is the angle? Minus 2 pi. So minus 2 pi is an even multiple of pi. It has to be an odd multiple of pi. So now we know that, but this minus 2 pi can never be an odd multiple of pi, right? It can never be an odd multiple of pi. It is going to be an even multiple of pi, right? So again, if the solution is, if I want the solution to be minus 2 and minus 3, then that solution is not going to satisfy the angle criteria. And since that solution is not going to satisfy the angle criteria, that solution cannot be a solution. Someone is saying why plus 0? Because that's a positive number, right? For positive real number, what is the angle? For positive real number, so 0.9. What is 0.9? If it's a complex number, then 0.9 angle 0 degree. 0.9 angle 0 degree, right? What is minus 1 really? So what is minus, for example, this one? What is minus 0.1? Minus 0.1 is 0.1 angle 180 degree. Okay, someone is saying, oh, why? Okay, nice. Okay, I gave you a plus 0, now you want a minus 0, no problem. Now, this is going to be true for any value of s between 0, so between minus 2 and minus 3. Okay, choose any value between those two. So, whatever you choose for the value of the gain k, roots can never lie here as well. Roots can never lie here as well. So, real line, the real part here, so real line here can never be a solution here. So, roots cannot be between minus 2 and minus 3, and roots cannot be between minus 1 and 0 here. Got it? Now choose any of these values. What about this one? Okay, between, I think you can understand I using the different inks, right? Green and red here. Okay, now choose a value between minus 1 and minus 2. Whoever does first. Minus 2 and minus, minus 1 and minus 2. Anywhere here. Minus 1 and minus 2. Choose any value between minus 1 and minus 2. What am I writing? I'm breaking mathematics somehow. Okay, already you are, so s equal to minus 1.9. again, that's gonna be true. That's gonna be true, right? Now let's just copy paste. All right, take our example. So that is what we are looking for. All right, so that has to be an odd multiple, right? Okay, oh, forget about that. That was 0 already. So this is minus. What about this angle? How much is it? How much is it? What is so again, I am not putting the particular value here. Just try to understand. If s is between minus 1 and minus 2, if s is between minus 1 and minus 2, that's going to be negative, right? If s is between minus 1 and minus 2, this number is going to be negative. Okay, but this is going to be positive. This is also going to be positive. If s is between minus 1 and minus 2, something like minus 1.9, that's going to be negative. These two are going to be positive. Okay, and as such, what about the angles? This is going to have an angle of pi. Okay, this is going to have an angle of 0 because it's a positive quantity. This is also going to have an angle of 0. So that's actually minus pi, and minus pi indeed is an odd multiple of pi, right? Minus pi indeed is an odd multiple of pi. Just put n equal to minus 1 here. Okay, minus pi indeed is an odd multiple of pi, and this is going to be true for any value of s between minus 2 and minus 1. Okay, minus 2 and minus 1. Now I will take your particular example, and I will, so essentially any value between minus 1 and minus 2 for s, right? If s is between minus 1 and minus 2, it satisfies the angle criteria. It satisfies the angle criteria. But does it also satisfy the amplitude criteria? Okay, right? In order for to be an actual root, it will also have to satisfy the amplitude criteria. So I'm saying if s belongs to minus 2 and minus 1, okay, again it's an open interval, okay, it satisfies the angle criteria. But does it also satisfy the magnitude criteria? UDE. Does it also satisfy the magnitude criterion? So we chose a value between this. What was the magnitude criterion? Magnitude criterion was the magnitude of GS HS has to be equal to 1 by k. But again, see how I posed the question. The question I posed here was, can I choose a value of k? Can I figure out a value of k for which the pole lies between minus 1 and minus 2? For which one of the poles lies between minus 1 and minus 2? Right? That was our question. So can we choose a value of k? And that is exactly what I'm going to do right now. I am going to choose a value of k and see whether I can choose a value of k. And if I can, then I would say that the amplitude criteria or the magnitude criteria has been satisfied. We already verified that the angle criteria is satisfied. So it satisfies the angle criteria. If the poles are between these, the angle criteria is satisfied. What about the amplitude criteria? So choose any. Okay, so what about this equation? How does this equation look like? So for our particular example, GSHS, since HS is equal to 1, GSHS looks like this. And that has to be equal to 1 by k, where k is a positive number, positive real number. Okay. So again, you know that if I multiply two or many complex numbers and take their mod, that's equivalent to taking their mod and multiplying them. Okay. So this is like mod 1 by s plus 1 plus times mod 1 by s plus 2. So these are products. Mod 1 by s plus 3, and that's gonna be 1 by k. So what is the value of k I chose? What is the value of k I chose? I chose a value of k between minus 2 and minus 1, but that doesn't matter because the moment I take a mod here, it's gonna give you a positive number, right? So that's gonna be here in this one. So you gave me minus 1.9, right? Someone gave me minus 1.9. Say s equal to minus 1.9. So if I put s equal to minus 1.9, so that's gonna be minus 0.9 times 1 by that's gonna be 0.1 times, that's gonna be 1 by 1.1. That's gonna be 1 by k. So of course k has a very fine solution, right? So here k is just going to be 0.9 times 0.1 times 1.1. So for this value of k, now we have figured out, for this value of k, one pole, at least one pole is at s equal to minus 1.9, because s equal to minus 1.9 satisfies the angle criteria, and also for s equal to minus 1.9 I can find out a positive value of k, which of course I can. Okay, so having s equal to, so we can say one of the roots is at, so we can say at least one of the roots, at least one of the roots is at or is at s equal to minus 1.9 if k is equal to whatever that product is, 0.9 times 0.1 times 1.1, right? And for any value between minus 2 and minus 3, that's going to be the case, because any value of s between minus 2 and minus 3 satisfies the angle criteria, and also I can figure out a value of gain k. Now, so try to understand how we are approaching the problem. Instead of solving the problem, we are trying to get certain insights on the problem, right? See, we did not even solve for the equation, did we? We did not. We did not solve for the equation, but we, instead of solving the equation, we somehow, without even solving the equation, did we solve the equation at any given point? No. But instead of solving the equation, without solving the equation, we still figure out a value of gain k for which a particular value of s is achieved. Okay, so s is going to be minus 1.9. At least we have one solution like that. S equal to minus 1.9 when gain k is equal to, someone is saying that's 0.099, right? So we figured that out. So when k is equal to 0.099, one of the roots is at minus 1.9. That's something we figured out pretty easily without actually solving the equation. At no point we employed Newton-Raphson or anything like that. We did not use a calculator to solve the equation really, right? But we figured out when k is equal to 0.099, one of the roots is at minus 1.9, and we can see this idea is going to be very useful, right? So let's go back to our earlier question. So any point, just like we figured out, any point between minus 1 and minus 2 would be on the root locus. Similarly, any point beyond minus 3, so any point to the negative side of minus 3, so essentially any point lower than minus 3, so minus 3 and anything beyond that, so minus 4, minus 5, any real number between those, okay, those will also be on the root locus. So yes, and this is confirmed by the root locus itself. Look at the root locus, look at the drawing, look at the very drawing. Okay, let me just do one thing. Let me just take the drawing here, rather copy it, paste it on a page like this here, and let's make this bigger. Now this, what I just said, what we just derived, is confirmed by the root locus itself. Look very carefully, is that the entire part between, so look very carefully here, the part between s equal to 0 and s equal to minus 1 is empty. So at no given value of k, the roots are between 0 and minus 1. Similarly, the part between minus 2 and minus 3 is empty. Okay, so for any given value of k, there cannot be any root between minus 2 and minus 3. Okay, but for certain values of k, I would have roots between minus 1 and minus 2, because this is the path that the roots took. So that's the root locus. The drawing in white here is the root locus, locus of the roots, right? So here also, for some values of k and k, which is greater than 0, of course, the roots can be between one of the roots, at least at here in particular one root is here, right? So this part on the real axis is on the root locus, this part on the real axis is on the root locus. Okay, now instead of checking by calculating and figuring out whether it satisfies the angle criteria or not, there is a very handy way of doing it, right? That's why we are saying rules or formulas, for example. So we are talking about rule number 2, root loci on the real axis. So I am stating the rule, and you will see it will pretty much comply with what we just derived. Okay, we derived something here, and what I'm stating right now is going to comply exactly with what we derived. So root loci on the real axis, I'm saying only those portions with odd number only those portions on the real axis. Hold on. Only those portions on the real axis, rather bad English, okay, only the portions Okay, location. Okay, fine. Someone is asking what is the difference between, okay, I'm talking about English terms, right? What is the difference between location and locus? The thing is, location is location at a point, and locus is locations, for example. Okay, the path a point takes. So I'm really currently looking into having an alternative ISP besides the current one I have. I have the hardware to make a bonded connection, so I really need to have a failover. I really need to have a failover. Right? I think it's back, right? Wow, the kid. Nice. All right. So this was the condition. So as we were saying, before I was rudely interrupted, we are saying, okay, as I was saying, someone asked me about the difference between location and locus. Okay, location. So locus is essentially the locations over time, right? So if you travel following, of course, when you travel, so you are tracing one point from another. So this is your source and this is your destination. You are starting from this point and going to this point, and of course you are, of course, when you from this point to this point, unless you are quantum teleported, you would have a continuous path, right? You would have a continuous path that starts from here and ends at here. So at any given point, given instance, whatever your position is, that's your location. And if I trace out the location over time, that gives me the locus. Now time is a parameter here. Okay, and in our particular example, time is not the parameter, but the gain is the parameter. So for a particular gain, if I give you the locations of the poles of the closed loop system, that would be root location, known as the pole zero map. Okay, and for ranging values of gain k, for a certain range of gain k, if I give you the root locations, then it becomes the root locus, or actually root loci, because we have multiple roots, right? So root loci really. Only the, so now here root loci on the real axis, I'm saying only the portions on the real axis having odd number of poles this is kind of becoming quite unfortunate and really annoying. So I'm getting intermittently interrupted. All right, so I think it's fine, right? So this is becoming really annoying. Okay, so in case you didn't in case you were not able to see this, okay, the webcam is somehow not working again. Oh. All right, hold on for a second. Right, after so many interruptions. Okay, so this is what I wrote last. Okay, saying only the portions of the real axis having odd number of poles and zeros to their right are parts of the root locus, and we did establish that. Okay, so if we take any point between these 2 points, okay, if we take any point between 0 and -1, now say, think about it in this way. Say you are a point and kind of human looking point, you are standing here. Okay, now look to your right. how many poles and zeros do you see? Okay, how many poles and zeros do you see? And how many poles and zeros do you see to your right? 0, right? So this part is not going to be on the part of the a part of the root locus. Okay, right? Now say you are standing here, right, and looking to your right. So you are standing between -1 and -2 on the real line and looking to your right. How many poles and zeros do you see to your right? How many poles and zeros do you see to your right? You see 1. And if you see 1 poles and zeros combined, total 1 poles or zeros, poles and zeros total. Okay, that's an odd number. So this part is going to be on the root locus. Now you are standing here, okay, looking to your right. How many poles and zeros do you see to your right? Rather, how many open loop poles and zeros do you see to your right? 2. 2 is an even number. 2 is an even number, right? So this part is not going to be on the root locus. Okay. Similarly, if you are standing here, looking to your right, how many open loop poles and zeros do you see to your right? Answer is 3. Okay, 3 is an odd number. So this part is going to be on the root locus. So this is essentially the same thing, saying that if you have odd number of poles to your right, essentially having poles to your right essentially gives me negative numbers here, right? So if I'm standing here, somewhere here, so this pole, so if s, so for example, if s is equal to -4, then of course this is going to be negative, this is going to be negative, this is going to be negative, this is going to be negative. So -180, -180, -180. Okay, so essentially I would have a positive 180 plus positive 180 plus positive 180. So it's a 3 times 180, so it's an odd multiple of 180 degrees, right? So essentially I need to have odd number of poles or zeros to my right, okay, to have odd number of negative terms appearing in this equation here. And since if odd number of negative terms appears here, then of course their angles would be 180 degrees. So I would have odd number of 180 degrees, and as such the angle criteria would be satisfied. But say if I am standing here, then I am seeing 2 poles to my right. So this one would contribute 180 degree, this one would contribute 180 degree, right? Because say for example AC is say -2.5. If AC is -2.5, then this part is going to be negative, this part is going to be negative. Sorry, this part is going to be negative, this part is going to be negative, but this is going to be positive. So I would have 180 degree plus 180 degree plus 0, and as such the total contribution would be an even multiple of 180 degrees. So essentially wherever I am standing currently, the poles and zeros that are on the right gives a 180 degree contribution, plus or minus. Okay, and if I am standing and whatever is the number of poles and zeros to my left, okay, those will have positive values encountered, so they will give me 0 degrees of contribution, right? So essentially whenever I am standing on the real line, I have to look to my right, and the number of poles and zeros that I have to my right will actually contribute to the total angle contribution. The number of poles and zeros that I have to my left, okay, will have 0 angle contribution, right? So I need odd number of pi, okay, odd multiple of pi, okay. So I would need odd number of poles and zeros to my right. So this is the rule number this is the rule number 3, right? Rule number 2. Now rule number 2 is pretty important, pretty useful, right? Let me give you another proper example showing you how that rule can be very easily used to example of rule number 2. Example of rule 2. Okay, see, say I'm just saying that I'm not telling you the transfer function just yet, but say you know that these are the pole locations, open loop pole locations, right? So say like this, right? Now if I ask you this question, is this part on the real axis, is this part on the real line part of the root locus? So would I be able to, so if I take any point between these two, would that be a part of the root locus? Do you understand my question? If I take any point between these two, would that be a part of the root locus? Answer is yes. It's very simple. I am standing here. I am standing here and looking to my right. How many poles and zeros do I see? Open loop poles and zeros do I see? I see just one odd number. So that part is going to be on the root locus. Okay. Now here, if I am standing somewhere here, look to my right. How many poles and zeros do I see? I see two, right? If I am standing here, how many poles and zeros do I see to my right? Two. So the angle contribution would be an even multiple of 1 is an odd number. Yes, 1 is an odd number, 0 is an even number. Anytime you divide a number, anytime you do an integer division by 2, if the remainder is 1, it's an odd number, right? That's how 0 is an even number. And now I'm standing here looking to the right. How many poles do I see? Poles and zeros do I see? I see 0. I see 2. So 2 is an even number. That part cannot be on the root locus. So this part cannot be on the root locus. So now here, look here. What about this portion? What about this portion? If I'm standing here, if I look to my right, yes, 1 is an odd number. 0 even, 1 odd, 2 even, 3 odd. If you stand here, okay, maybe I think you are getting confused with prime numbers, right? 1 is not a prime number. Okay, 1 is a composite number actually. There is, in mathematics, there is something called a principle of void satisfaction. Sorry, what am I saying? What about 2? Imagine 2. Is it a prime number or a composite number? And what about 1? Is it a prime number or a composite number? By definition, see, yes, 1 is composite. Of course, 1 is composite. So 1 is a composite number. Really, 1 is not a prime number. 1 is a composite number. 1 itself is considered to be a composite number. Right? Because the idea is, why is 5 a prime number? Because 5 is divisible by 5 and 1. Anything between those two numbers does not divide 5, right? So that's how 5 is a prime number. But what about 1? There is nothing between 1 and 1, right? There is nothing between 1 and 1. So you cannot say that 1 is not divisible by anything between 1 and 1. So that statement is absurd. And since that statement is absurd, there is no other way but to designate 1 as a composite number. So 1 is considered to be a composite number. Okay? But we are not talking about composite number, prime numbers. We are saying odd numbers and even numbers. I think that's much easier than that. Right? So we are standing here. Say we are standing here. So is this part on the root locus? Is this part on the real axis on the root locus? No. That part is not going to be on the root locus, because if I'm standing here, if I look to my right, I would see that there are even number of poles and zeros to my right. So this part is not going to be on the root locus. So that part is not going to be on the root locus. Okay. Now what about this portion? What about this portion? Okay. So if I'm standing here, I would see that I have even number of poles and zeros to my right, open loop poles and zeros to my right. So this part on the real axis is going to be a part of the root locus. So right off the bat, without actually solving for anything, I know what I can solve for, right? That's an example. Let's take another example. Okay. Let's take another example. Now open loop poles can be on the right half plane. Let's say I have open loop poles here. Hold on. Very difficult root locus, right? It's going to be really, while calculating this, this is what is the order of the system here, what I just drawn. What is the order of the system? All are poles. I'm just writing all to be poles, but there can be open loop zeros as well. Okay, we're going to talk about that, talk about the generalization later. Okay, so it's a very complicated system. How many? 3, 3, 6, 7, 8. It's an 8th order system, right? But still we can very easily figure out what parts of the real axis are on the root locus, right? So this is again the denoting the open loop poles here. All right, so now let's take this, and I'm saying, okay, just one more thing that I somehow forgot to mention. Okay, if I'm standing here on the right half plane here, if I'm standing here on the right half plane, can the real part of the right half plane be on the root locus? Similarly, if I'm standing here and looking to the right, of course I see there are no poles, so 0. I see 0 number of poles to my right. So the right half plane cannot be on the root locus, right? Here. So the real part of the right half plane cannot be on the root locus. That was the point. Similarly, if I'm standing here in this example, looking to the right, I see 0 number of poles and zeros to my right. So again, the real part of the right half plane cannot be on the root locus. So if the system becomes unstable for a certain value of gain k, then the poles will be complex conjugate pairs. I cannot have real positive pole. I cannot have real positive pole making the system unstable. I can only have a complex conjugate pole pair, complex conjugate pole pair on the right half plane making the system unstable. I cannot have real positive poles making the system unstable because this part of the real line cannot be on the root locus, right? Because of the angle criteria once again. Okay. Similarly, here, if I look at here, so if I stand somewhere here, okay, I do not see any pole to my right. So even number of poles to my right, poles and zeros to my right. So that part cannot be on the root locus. So again, this portion cannot be on the root locus. So I'm just drawing the portions that can be on the root locus. So this entire portion can be on the root locus. See, if I'm standing here, how many poles and zeros do I see? 3. If I'm standing here, how many poles and zeros do I see to my right? 5. So this entire portion here can be on the root locus. Okay. Now here this cannot be on the root locus, but this portion can. Okay, if I'm standing here, I see 6 number of poles and zeros to my right. Okay, and hold on a second. Oh, this portion cannot be. Okay, only this part of the real axis can be on the root locus. Right, only this part of the real axis can be on the root locus. So even if I give you a very complicated system, you can still figure out under what conditions the roots are real, right? Roots are real. Under what condition the roots are real. Okay, so you can figure this out very easily at least. Alright, I think that's fine, right? Okay. So we would end with one more rule, and we saw, if you recall this plot again, we saw that this pole was approaching this direction and this pole was approaching this direction, right? And they met at a certain point. We are now looking into that point where they actually had met. So there was a value of gain k. So this is what we are trying to figure out. We're trying to figure out at what gain k two roots were equal. So this root was approaching in this direction and this root was approaching in this direction, and at a certain value of gain k they actually met, right? They actually met. So we are trying to figure out at what gain exactly they met, right? So let me just go to this Python program that I did just in the morning, and let's just say switch over to this. All right, and let me just modify this a bit. Let's make this 0.5, and let's make the step size 0.1. All right, so now look at this one. So k was this. So this root, if I increase the value of gain k, this root which approached in this direction and this root would approach this direction, right? So let's increase the value of gain k. See, very slow, very slightly, these two roots are approaching this, and of course this root is going in this direction again. So this portion of the real line can never be met. As I keep on increasing the value of gain k, See, these two roots are approaching each other. Okay, so somewhere between 0.38 and 0.39, see, somewhere between 0.38 and 0.39, these two roots are meeting and then diverging from each other. So we are looking for that particular point at which these two roots coincide. We are trying to figure out that point. So that is going to be the last thing we do today. Okay, so let's figure out our rule number 3, right? So rule number 3, we are trying to figure that out right now. So rule number 3. So before I talk about rule number 3, so again, the name for this particular one is breakaway or break-in points. Just keep in mind, the name is this. Breakaway, break-in points. Okay, so now try to understand what equation we are solving. We are solving for this equation, s cube plus 6s square plus 11s plus k plus 6 equal to 0, right? We are solving for this equation, and we know that there is a value of k between 0.38 and 0.39. There is a value of k between 0.38 and 39 for which this has two equal roots. This has two equal roots, right? Now, with that said, let me ask you a very simple question. If I give you a function of x, let's talk about your school algebra. If I give you a function of x and I say that this function of x looks like this, x minus 2, x minus 3. Now ask you, what are the roots of this function? What are the points? What are the zeros of this function? What are the points at this function what are the points at which this function becomes 0? Right? Or rather, let me ask you this question slightly differently. You just saw the function, and if I say I have a function fx and I know if f2 is 0 and f3 is also 0, so you know, at the very least I have a factor like x minus 2 in here, x minus 3 in here. There could be other things multiplied with this, there could be other things multiplied with this, but at least these two would be there. Otherwise this cannot happen, right? Otherwise this cannot happen. So if I say fx equal to a function of x, then and also tell you that f2 is 0 and f3 is 0, then you know that there must be a factor of x minus 2 and x minus 3 in the function, right? Otherwise this cannot happen, right? This cannot happen, right? Please let me know that you understand what I'm saying here. Again, let me just put a certain space here. That's fine, right? I think that's fine. Right? Some factors will be there, some factors will be there, and just like all right. So no confusion there, right? But the problem is, if I have a function that looks like this, that would still satisfy this equation, right? That would still satisfy this equation. If I have a function that looks like this, that still satisfies this equation, right? So essentially I know that there is a factor of x minus 2 and x minus 3, but how many factors of x minus 2 and x minus 3 I have, I do not know, right? So I know that there is a factor of x minus 2 and there is also a factor of x minus 3, a factor of x minus 3, but I do not know how many factors there are. How many factors of x minus 2 there are, I do not know. I do not know. Question is, how can I figure out that how many factors of x minus 2 there are, how many factors of x minus 3 there are? To understand that, let's take a very simple example. Instead of all these, let's forget all this. Let's take a very simple example, right? Simple example here. All right, let's take a very simple example. I mean, forget the factors here. Okay, if you have factors, doesn't really matter. Okay, doesn't really matter. Just now let's differentiate this. So I'm looking for how many. I'm looking for these numbers. How many roots are at x equal to minus 2? So I can see there are 2 roots at x equal to minus 2. This is becoming 0, but not for one root, because of 2 roots, right? So this has two components like that. Now what about the first derivative of x, first derivative of f, right? What about the first derivative of f? So I say that becomes something like this, right? Right, something like that, first derivative of this. Now what about this, what about f2 here, sorry, what about f dash 2? What is the value of the first derivative of f, first derivative of f when x equal to 2, x is equal to 2? So that is 0, this is 0, so this is 0, right? What about f dash 3? What about f dash 3? F dash 3 is also 0, right? Sorry, here is a cube. F dash 3 is also 0, right? No problem, right? I think there is no problem, right? Right, no problem. So I told you this. Now let's do the second derivative here, right? Now if I do the second derivative here, look carefully what happens. If I do the second derivative here, I have to differentiate this. Let's do that. So that becomes 2 x minus 3 whole cube plus 6 x minus 2 x minus 3 whole square plus 6 x minus 2 x minus 3 whole cube, and then I have plus 9 x minus 2 whole square x minus 3, right? That's the second derivative. Right, now if I ask you this, what about f double dash 2, and what about f double dash 3? So f double dash 3 gives you 0. See, if you put x equal to 3, this becomes 0, this becomes 0, this becomes 0, this becomes 0, that's 0. But what about f double dash 2? If I put x equal to 2, will it become 0? Sorry, yeah. So that's gonna be 2. Right. So that's gonna be 2. Hold on for a second, just a second. So yeah, sorry, this has to become 2. Okay, I made a mistake here, and this has to become a 2, and subsequently, I'm really sorry, I made a calculation mistake, right? 6, and that's also gonna be 6. Okay, yeah. So I made a mistake in the first derivative, but my point stands. Okay, if I take x equal to 2, that's the it's a 0, and if I take x equal to 3, that's a 0. But if I take the second derivative, if I put x equal to 3, this is still 0. But if I took the second derivative and put x equal to 2, see, this is a non-zero. So this is not 0. Not 0. Now I have a function. Now I have a function for which I know really how many roots there are at x equal to 2. See, try to understand that in the original function I had 2 factors of x equal to 2. So when I differentiated that, right, one of the factors got reduced. If I differentiated once again, the other factor got reduced once more. So here, what is the lowest power of x minus 2? In this equation, in this polynomial, the lowest power of x minus 2 is 2. That is why I said it has a factor of x minus 2 times. But here, what is the lowest power of x minus 2? That's 1. So it has a factor of x minus 2 but once. But here, what is the lowest power of x minus 2? 0. Right? There is a factor where you don't have x minus 2. Now here, so we have a polynomial for which we have a this is the polynomial, right? We have a polynomial for which f2 is equal to 0, f dash 2 is also equal to 0, but f double dash 2 is not 0. So from that we know that there are 2 roots at x equal to 2, right? We know there are 2 roots at x equal to 2 because when we differentiated once more, when we took the second derivative, that particular root got eliminated, right? That x minus 2 factor got eliminated because of the differentiation. So now if I take a polynomial and keep on differentiating it, okay, the number of times I was able to differentiate plus 1 becomes the number of roots at that point. So again, I would be able to differentiate it once more, and if I check that whatever it is, so f triple dash 2, that's not 0, I know, and f triple dash 3, that's also not going to be 0. So from this I know whenever the derivative becomes non-zero, like that, okay, I know that many roots I had. So from this idea I know that the derivative of f, so basically f double dash 2 becomes non-zero. Okay, so for the first time, so we had f2 equal to 0, f dash 2 equal to 0, but f double dash 2 is non-zero, which indicates the factor of x minus 2 had a power of 2. Similarly, I know f dash 3, f3 was 0, f dash 3 was 0, f double dash 3 was 0, but f triple dash 3 was not 0. So I know the factor of x minus 3 I had a power of 3. So by that idea, I now know how many roots I have at x equal to 2, how many roots I have at x equal to 3. Okay, and that is the idea we use in calculating the breakaway and break-in points. Okay, so what we do, we take this polynomial, we take the polynomial here, and this polynomial, if it has, so it's a polynomial, right? If it has two roots at a point, then the first derivative is going to be 0 at that point. Say for example, I'm saying try to understand. No, I'm just checking whether there are 2 or more roots, right, at a point. So if at s equal to s1, there are 2 coinciding poles, basically 2 identical roots, then the derivative of this, right, try to understand, the derivative of this, okay, the derivative of this will have to be 0, right? Now what am I differentiating? Whose function is this? What am I differentiating really, right? Whose function is this? So this is equal to 0, right? Let me just write it down once again, right? So whose function is this really? What is the dependent variable? What am I going to differentiate with respect to, right? So I can write this as k equal to minus s cube plus 6s square plus 11s plus 6. So it's really, so this is like y, right? So essentially it's like saying y equal to something like this, and everywhere I took a derivative, it was like derivative with respect to x, derivative of y with respect to x. So here the same thing, we are going to differentiate with respect to s, but what am I differentiating? I'm differentiating k, right? I'm differentiating k. So I want to make k, so basically I want to see whether there are double roots in s, right? Just like that, we differentiated with respect to x, but what did we differentiate? We differentiated y. Just like that, we are going to differentiate this. So here I'm saying if at s equal to s1 there are 2 coinciding poles, then rather let's just say s at sb, let's say sb, okay, breakaway break-in points sb. So if at s equal to sb there are 2 coinciding poles, so essentially I would have 2 poles, sb both, right? Then del k del s, I'm writing del k del s because writing partial derivative is a better option here. There could be other parameters, so you can imagine that it has dk ds equal to 0 at s equal to sb. So the point is that if there are more than one roots, 2 or more, rather I would say 2 or more coinciding poles at this point, then the derivative is going to be 0, right? At least, right? So let's now differentiate this. So take a minus sign. I have 3s square plus 12s plus 11, and we know del k del s at, so implies del k del s at sb, that's going to be minus 3sb square plus 12 sb plus 11, okay, right? So now this has to be 0, right? This has to be 0, right? Now if there are more than one pole at S equal to SB, then del K del S or dk ds, whatever it is, okay, at SB, that's equal to 0, which means this equation has to be 0. Of course, we can disregard the minus sign. So we get 3SB square, and you can write just S. No one is going to bother you, right? Really. 12SB plus 11 equal to 0. Alright. So that's a quadratic equation. Solving quadratic equation is not a difficult task. Say S equal to minus B plus minus root over B square minus 4AC. So that's going to be 144 minus 4AC, right? So okay, that's going to be 11 times 12, right? Please do the calculation independent of me, because I am really good at calculating things. Let's see, that's going to be 12 132. That's your quadratic formula by Shidacharya, right? So by 2a by 6. So these are the two possible values. So two possible values for the breakaway or break-in points. So two possible values for S, for which the roots are real and equal. Here in this one, roots are real and equal. So I have minus 12 plus minus, but what is this one? That's going to be 12, right? Root over 12 by 6. Can somebody help me by doing the calculation? I'm going to get two values here. Again, I am writing a partial derivative simply because there could be other parameters, which we will say later on. Alright, can somebody help me out? Or I can bring up my calculator, right? Okay, you can see me struggling with the calculator, but let's see how well I go. Okay, let me just do the simplification, because at the end of the day, we can do certain simplification before we take the help of our calculator, right? But again, keep in mind that this kind of calculations can be done without a calculator. That is the point here, very easily, right? So that's going to be 2 root 3 by 6. So this is like, if I take out 2 at least as a common factor, that's going to be minus 6 plus minus root 3 divided by 3. Again, I know what is the value of root 3, right? That's 1.732 plus minus 1.732 divided by 6. Yeah. So now, can somebody solve it, please? Otherwise, I have to do the calculation myself. Minus 6 minus 1.732 divided by 6. That's going to be minus 6 plus, let's take a bracket, minus 6 plus square root of 3 divided by 6. Okay, so one of the roots is at minus 0.711, minus 0.711. The other one is at, please confirm that I am doing it correctly, because I might make mistake. Another is minus 1.289 minus 1.1 minus 1.289. Okay, did I make a mistake? What mistake did I do? Oh, sorry, divide by 3. What am I doing? It has to be divided by 3. Right. Thanks very much. Okay, when I had the calculator on my face, I was just seeing 6. That is why I wrote 6. Really good. So what are the solutions? And that is why I say that I really do not do any calculation by hand. Okay, I always take the help of a computer while doing calculations, because I do not trust myself with calculations. Minus 1.422 minus 1.42, that's fine. And what is the other one? Minus 1.42 and minus 2.58, right? We find that one. Right. So these are the two solutions, right? So at s equal to minus 1.42 and minus 2.58, there can be more than two roots. Unfortunately, one of them is an invalid point. One of them is an invalid point. Can someone figure out which one of these is an invalid point? So essentially, by differentiating and equating it to 0, I know these can be two possible roots, two possible values of s where two roots coincide, but one of them is invalid. One of the solutions here is invalid. Which one? So one of the solution is at minus 1.42, the other is at minus 2.58. Let's look at this. This was our root locus, right? So I know one of the solutions is at minus 1.42, right? Minus 1.42. So that's here. So that is the point here. That is what we are looking for. So this is that point. So this is at s equal to minus 1.42. So I know where these two roots are meeting. Okay, these two roots are meeting. But the point minus 2.58 is invalid. Minus 2.58 is invalid because it is a part of the real line which cannot be lying on the root locus. If s equal to minus 2.58, then it violates the rule number 2. Rule number 2 says, wherever I am standing, I need to be able to see odd number of poles and zeros to my right to satisfy the angle criteria. We got s equal to minus, but this root s equal to minus 2.58, this does not satisfy the angle criteria. This does not satisfy the angle criteria. So it does not satisfy the angle criteria. Satisfy the angle criteria. So that is not a valid solution. Okay. So I'm saying I'm writing this and then cutting this out to make sure that you understand. So at s equal to minus 1.42, there can be more than two roots, right? Because that is not satisfying the angle criteria. All the rules play together, right? I just need to know the gain k at which this is true. So I also need to calculate the gain. How can I calculate the gain? I can very easily calculate the gain because we already did somehow. How exactly did we calculate the gain? Because I can calculate the gain always through this equation, right? Through this equation. This is the magnitude criteria, because I need to satisfy two equations all at the same time. This is this is one equation, this is the other equation, right? So at this point, what is the value of the gain k? So I know and when, of course, I see there are two roots meeting at this point. When s is equal to minus 1.42, I know 1 by k is going to be mod of 1 by s plus 1, s plus 2, s plus 3. That's the magnitude criteria. That's the magnitude criteria. But we can also, since see, we started with this equation k equal to something like this, you can also put the value here. But instead of putting the value here, this will give you the same result as this one. Okay, instead of putting the value here, I really like to put the value here. So I have mod of 1 by, so minus, so if I put s equal to minus 1.42, so I would get minus 0.42 times okay, 58, right? 0.58 times 1.58. So mod of that. So multiply these three numbers and get rid of the minus sign, and then take a reciprocal. Then take a reciprocal, whatever is this. Then take a reciprocal. Therefore, k, what is the value of k? So this is 1 by k, right? Someone please calculate the value of k and let me know. Minus point, sorry, that's 0.385. So this is 0.385. And from our Python program, we did see that between 0.38 and 0.39, the roots were meeting and diverging from each other. So between 0.38 and 0.39, so that's 0.39 and that's 0.38. So at 0.38, they are just apart on the real axis, and at 0.39, they met and they diverge, right? So if I say 0.385, if I manually enter the value, you see these two roots are coinciding with each other. When k is 0.385, these two roots are coinciding with each other. That's the value at which that's the value of gain k at which these two roots are coinciding each other. Oh, I did not change this, right? Right. So as you saw already, between 0.38, between gain 0.38 and 0.39, the roots just met and slightly diverged, okay, and started diverging. So if I put 0.38, there they were, okay, meeting, approaching each other from the real axis. So at 0.385, so at k equal to 0.385, these two roots are coinciding here. Got it? That is something we figured out. So again, so let me just go back and say that at this point k was 0.385. So far, what have we known about the system? So rule number 3, let me write down the rule number 3. Rule number 3, breakaway and break-in points. Okay, we already, I think we wrote this, right? Didn't we write this? Okay, we say the points where two or more roots can meet are calculated by solving LK LS equal to 0. The solutions that satisfy the angle criteria satisfy the angle criteria. The solutions that satisfy the angle criteria are valid breakaway or break-in points. Okay, now we say breakaway and break-in points, they pretty much are the same thing, just there is a small distinction here. This one you are seeing is a breakaway point, not a break-in point. Okay, breakaway means they meet each other from the real line like this and then diverge from each other. They were approaching each other and then they diverge from each other. Okay, so that's kind of a breakaway. Okay, breakaway means they approached each other like this and after meeting they started diverging. Okay, that's kind of a breakaway point. Okay, the break-in would be something slightly the other way around. If the poles were approaching as complex conjugate pairs, if something like this happened, they were approaching as complex conjugate pairs. Okay, so they approach like this, and after meeting, they became real poles, and then something like this happened. So then I would call it a break-in point. Okay, okay, and also there is another distinction. Break-in can only happen after a breakaway of some sort. Okay, so if after diverging, if these poles meet at a later value of gain k, then I would say that point is a break-in point. But the condition would be the same. Okay, the moment I have two identical roots or more identical roots, the derivative of k with respect to s is going to be 0 at those points. Right? So that's the distinction. We are going to look into that distinction elaborately later on. Okay. So that is up to rule number 3. I was supposed to tell you up to rule number 6, but unfortunately, due to lack of time, I cannot. So that's the end of discussion today. Okay, we're going to continue this further, and we're going to learn quite a lot. Okay, so again, you can see that with this approach, we have so far gathered quite a bit of knowledge about the system without actually solving for the exact values of the poles. So we know so far that the system behaves like a overdamped system, right? So I would have real and unequal poles, unequal poles for s for k between 0 and 0.385. So the system is stable, I know. Now we see these are the insights we have. If k is between these value 0.385 and 0, we have real and unequal poles, right? So we call this overdamped system, right? So we have learned a few things about the damping nature of the system, right? And we also know at k equal to 0.385, there are two roots on the real line coinciding with each other. So that should be a critically damped. So we already know a little bit about the damping of the system. Yes, someone is asking, are we going to get a special Google Meet class? Yes, we are going to do that tomorrow, I think. All right. So that is something we have gathered so far. We are going to continue with this. As I said, there will be 3 classes on this on total, and that will be the end of today's discussion. If you have any question, feel free to ask. Otherwise, we are going to end it right now. So thank you very much for being patiently here, and we have a lot to discuss later on. We'll see. I will see you tomorrow. All right. So thank you very much. Oh, and I will see you. I will show you tomorrow how to do this using Python. It's a very easy thing, right? It's a very actually easy thing. Just to tell you, in case, just wait for 5 more minutes. You have already waited so long. Just wait 5 more minutes. I can show you how actually you can do this. Do this using Python. Okay? Let me just increase the font size. It's a very simple thing. Let's just write down the transfer function. So G was CT control. We have to import the control system library. Control dot transfer function. We have 1. Okay, we are taking care of k, for example, right? And we have 1 1 6 11 6 0. So that was the transfer function. Let's just say this is the transfer function. We know that transfer function G, right? That was the transfer function. Okay, not this. I mean this. Sorry. Yeah, this was the transfer function, and all we need to do is to do control, then r locus, stands for root locus, r locus G. Just do that. Okay, they will give you. Okay, just do this. I mean, this is showing you so many things. Just put a semicolon after this. Oh, thank you. I made the same mistake once again. Okay, you have to import the control system library first of all. Import control as something, say CT. After that, you already know how to define transfer functions, right? Define the transfer function, right? Okay, define the transfer function, and this is the transfer function apart from the k, right? Sorry for that. Okay, so you have this, define the transfer function. You know there are many ways of defining transfer functions, and once you define the transfer function, you can call the root locus function. See, and it also showing you the S grid. It is also showing you the S grid alongside. Okay, so again you can see that these are the open loop poles here, one at -1, one at -2, one at -3. And as the gain increases, this pole goes to this direction, this pole goes to this direction, this pole goes to this direction, and from there they diverge like that. And there are so many things we can actually figure out about this. Okay, it's a very small, very simple thing. Define transfer function and call the root locus function on it. Okay, control dot r locus, just give it the transfer function. Just give it the transfer function. Okay, give it g. Just keep in mind, you need to give it this transfer function. Okay, this one instead of the k. Okay, apart from the k, you have to give it this 1 divided by whatever it is. You're going to do that. So I think that will be the end of today's discussion. So thank you very much. It was a very simple but yet useful discussion, I believe. Okay, so thank you. I will see you tomorrow.